All right, so get ready to dive into a super cool world. We're talking superconductors. Literally and figuratively, we're diving into this paper by A.V. Nikolov. And let me tell you, this thing throws some serious curveballs. It really questions some of the bedrock ideas in physics.
Yeah, what's really fascinating about it is that it all kind of stems back to something called the Meissner effect.
Yeah.
Which has been puzzling physicists for the better part of a century.
Yeah, so for people who aren't familiar, picture a magnet just kind of floating above a superconductor, like something out of a sci-fi movie, right? That's the Meissner effect in action. It's this idea that the superconductor is essentially saying, nope, not having any of that magnet stuff, and it just repels it.
Yeah, and what makes it even more interesting is it's not just an electromagnetic phenomenon, right?
That's right.
It's considered a macroscopic quantum phenomenon, meaning we're seeing quantum weirdness, which usually happens at a tiny scale, playing out on a scale that we can actually see and interact with.
Yeah. Okay, now here's where it gets really, really interesting. The way that we typically explain this Meissner effect seems to clash with some other, very, very fundamental laws of physics, like the conservation of angular momentum and even the second law of thermodynamics. It's like these superconducting electrons are playing by a whole different set of rules.
Yeah, that's a really good way to put it. The Nikolov paper really kind of gets into the thick of it. He even calls out some pretty big names in the physics world who've been sort of wrestling with these apparent contradictions. He mentions Jorge Hirsch, who's been very vocal about these sorts of things.
Yeah. Okay. So to understand what's so groundbreaking about all of this, we need to break down the Meissner effect a little bit. So imagine like a dance floor, right? And normally on a dance floor, it's crowded. People are bumping into each other. There's some friction going on. But now imagine the dance floor suddenly becomes frictionless. Everyone can just glide effortlessly. That's kind of like what's happening inside of a superconductor. Electrons can suddenly move with absolutely no resistance whatsoever.
Yeah, that's a perfect analogy. So we've got our superconducting dance floor. Our electrons are waltzing around with zero friction. Now let's say a giant disco ball descends upon the dance floor. This is our magnet.
Right. In a regular material, in a non-superconductor, that magnetic field from the disco ball would just pass right through. But with a superconductor, a very different thing happens. Those electrons are like, disco ball, nope, not happening. And they start flowing in a very specific way that creates their own magnetic field.
And this magnetic field that they create is perfectly opposed to the disco ball's field, effectively pushing it away. That's how you get the levitating magnet. It's pretty wild.
Yeah, it's amazing to see, but it also presents this big puzzle of what the paper calls the action at a distance problem. It's like those electrons somehow sense that approaching magnetic field, and they start preparing to repel it before it even gets close. It's like they're doing their thing before the disco ball even touches the dance floor.
Yeah, it's as if they have like a sixth sense for magnetism. So these big sort of mysteries surrounding this whole thing, that kind of challenges our typical understanding of how physics works.
Yeah, you would think quantum mechanics would have an answer to this, right?
Well, quantum mechanics is very good at describing the world at the really, really small scale. But things get a little bit more complicated when you try to scale those rules up to something that we can see and interact with. It's like trying to explain the behavior of one ant versus trying to explain the behavior of an entire ant colony.
Yeah, so that's where we get to Bohr's correspondence principle, right? Like this idea that quantum mechanics should smoothly transition to classical physics as we go to larger and larger scales. No weirdness, no contradictions.
Exactly. And they use this really interesting example in the paper to illustrate this. Think about persistent currents in normal metal rings. This is this weird thing where electrons in these rings just keep on flowing in circles for a surprisingly long time, almost like they're defying resistance.
So we've got tiny perpetual motion machines happening at the atomic level.
In a way, yeah. But the key thing here is that the energy changes involved are super small, right? Yeah. We're talking microscopic quantum stuff. But with superconductors, the energy changes associated with these persistent currents are huge in comparison. These aren't just tiny fluctuations anymore. This is macroscopic quantum behavior. And this really throws a wrench in the whole correspondence principle.
So it's like the superconductor is acting like this giant atom with electrons in these massive orbits, totally defying what we thought we knew about quantum behavior.
Exactly. And they make a direct comparison. A superconducting ring with a macroscopic radius behaving like an atom with a tiny radius. And that's where our current understanding really starts to break down.
Okay, so if our usual quantum playbook is not working here, what do we do?
Well, back in 1941, this physicist named Lev Landau came up with a really revolutionary idea. He said that to actually understand superconductors, we can't treat electrons as individual particles, even though they are.
Wait, what? How can you have an electron that's not acting like an electron?
It's pretty wild, right? He proposed that in the world of superconductors, electrons were pairing up, forming what we call Cooper pairs. And these pairs, they don't behave like two separate electrons. They act as this single unified entity, almost like a new particle.
So going back to our dance floor analogy, it's like instead of individual dancers, now we suddenly have all the dancers pairing up, and they're doing this perfectly synchronized waltz moving as one.
That's a great way to put it. And this synchronized dance of Cooper pairs. This led to the development of the Ginzburg-Landau wave function, which is different from the typical Schrödinger equation that people might know, which describes the probability of where a single electron might be. The Ginzburg-Landau wave function actually describes the behavior of all these Cooper pairs together as one.
So Landau's big breakthrough was recognizing that these electrons, through this Cooper pairing, were behaving as one giant macroscopic quantum entity. That is mind-boggling.
It really is. And it has huge implications for how we understand superconductors.
Yeah.
But perhaps even more intriguing is how this idea might be related to another cornerstone of physics, thermodynamics, and specifically the second law.
Thermodynamics, the second law. Okay, so this is where things get really, really mind-bending. Because if we're talking about these huge persistent currents in superconductors, and those are somehow tied to this macroscopic quantum behavior, well, that has some pretty wild implications for energy, right?
Oh, absolutely. I mean, thermodynamics at its core is all about how energy behaves.
Right.
And one of the most fundamental principles of thermodynamics is this idea that everything tends towards disorder, right?
Yeah.
Towards some kind of equilibrium, like energy dissipates, things fall apart. Like think about your coffee mug shattering when you drop it on the floor. We don't typically see that process happen in reverse.
Yeah. Now shattered coffee mugs magically reassembling themselves. But with superconductors, it's like we're getting these glimpses into this other reality, this reality where maybe energy isn't quite as bound by these rules as we thought.
Exactly. And the paper really hits on this point. It says that when a superconductor goes back to its normal state, right, those persistent currents, the ones that are carrying all that energy, they should disappear. And that energy has to go somewhere. The most likely outcome, according to our current models, is that it would be released as heat.
Release the heat, right? Like a surge of energy as the superconductor powers down. But that's not what we see, is it?
That's the really weird thing. This expected heat dissipation, the one that should be there. It hasn't been definitively observed. And what's even weirder is this isn't a new problem. The paper actually goes into the history of this, talking about physicists like W.H. Keesom, who are already kind of wrestling with this apparent contradiction back in the 1930s.
So for decades, physicists have known about this weird discrepancy, this missing heat. But no one's been able to fully explain it. It's like the universe is playing hide and seek with energy.
Yeah, it's like the energy is just gone, vanished. And this really challenges our assumptions about how things work. It really makes you wonder, could the Meissner effect, this macroscopic quantum phenomenon, could it somehow allow for a violation, or at least a bending of the second law of thermodynamics?
Okay, now we're getting into some really mind-blowing territory. The second law, I mean, that's like a pillar of physics. Are we saying it might not be as ironclad as we thought?
Well, the paper doesn't come right out and say the second law is wrong. But it definitely raises some really interesting questions about how universal it really is. You know, maybe, just maybe, there are these scenarios, particularly when we're talking about these macroscopic quantum phenomena, where the second law doesn't quite work the way we expect. Or maybe there are these loopholes we haven't even considered yet.
Loopholes in the laws of physics now, that's exciting. But where do we even start to look for these loopholes? What are the missing pieces of the puzzle here?
Well, the paper offers a few interesting clues. One of them is this whole mystery of the crystal lattice within a superconductor.
Okay, the crystal lattice. Remind me, what exactly is that again?
Yeah, so think of the crystal lattice like the scaffolding of a building. It's this underlying structure of atoms that makes up the superconductor, provides the framework, the stability. Now, when those Cooper pairs start doing their synchronized dance, right, whirling around with no resistance, you'd think they'd interact with that crystal lattice somehow, cause some sort of disruption.
Yeah, it's like having a massive dance party inside of a perfectly built house of cards. You'd expect things to get a little messy.
Exactly. But that's not what happens. The crystal lattice seems to be totally unaffected by this electron frenzy going on inside of it. It's as if those Cooper pairs are dancing in a different dimension. Their movement completely decoupled from the structure of the superconductor itself.
That's bizarre. So you've got these two separate worlds, like the macroscopic quantum world of the Cooper pairs and the more classical world of the crystal lattice, just coexisting, not even interacting with each other.
It's like there's this invisible wall, this disconnects, preventing them from interacting the way we'd expect. And this really raises some profound questions about the nature of energy, about how these different levels of reality can exist and potentially influence each other.
This is blowing my mind. Every layer we peel back just reveals more mysteries. It's exciting and terrifying at the same time.
It gets even weirder. The paper also talks about something called the DC voltage puzzle.
The DC voltage puzzle. Okay, you've got my attention. What is that?
So basically it refers to observations of superconducting currents, the ones flowing without any resistance, seemingly moving against an electric field. Like imagine a ball rolling uphill effortlessly. It defies intuition.
So not only are these superconducting electrons potentially breaking the rules of thermodynamics, they're messing with electricity too.
In a way, yeah. And it's this defiance of expectations, this willingness to color outside the lines, that makes this research so interesting. It's really pushing us to rethink what we know, to be open to the possibility that our understanding is just a tiny glimpse into a much bigger, weirder reality.
It's almost like these superconducting electrons are giving us a peek into a world where the impossible might be possible, a world where perpetual motion isn't just a pipe dream.
Now that is a fascinating thought, isn't it? Perpetual motion, this holy grail of energy production, something we've always been told is impossible. But this paper, by highlighting these anomalies, these potential loopholes, it makes you wonder if maybe our definition of impossible needs a little bit of revising.
Perpetual motion, it's like the ultimate what-if question when it comes to physics. Are you saying that these weird things we're seeing in superconductors, like that missing heat or that DC voltage puzzle, are maybe pointing to a world where perpetual motion isn't actually impossible?
It's definitely a very interesting thought, and the paper really digs into this idea. What's so cool is that it's not just about finding some magic loophole to get free energy. It's more about realizing that maybe our whole understanding of how energy works, like how we get it, how we store it, how we move it around, is way more limited than we thought.
So we're not talking about breaking the laws of physics. We're talking about finding a whole new level of physics, a whole new set of rules where stuff like perpetual motion might actually be possible.
Exactly. And this is where this Nikoloff paper gets really interesting, really bold. It basically says that scientists not being willing to even think about these other possibilities, these challenges to what we think we know, is actually holding back science.
It's like that saying, if you're not questioning things, you're not really thinking. It's just so easy to get comfortable with the way we think things are, to just dismiss anything weird as a mistake or something we'll figure out eventually.
It's definitely human nature to want to be certain about things. But if you look at the history of science, there's so many examples of those little things that didn't quite fit, those anomalies, that ended up completely changing how we understand the universe. Take Einstein's theory of relativity. It totally shook up centuries of physics. But it gave us a much deeper and more accurate understanding of how the universe works.
So this paper is kind of calling for that same kind of revolution, but this time it's about how we think about energy.
In a way, yes. It's really about being more open to what we don't know, to those things that seem contradictory, and remembering that what we know about physics right now is amazing, but it's probably not the whole story. There might be whole chapters we haven't even discovered yet.
That's what's so exciting about this. It reminds us that science isn't about memorizing a bunch of facts. It's about always asking questions, exploring, and pushing the boundaries of what we think is possible.
Exactly. And who knows what amazing things we'll find when we finally get the courage to look beyond what's familiar, to follow those little anomalies, those hints of something more, even if they make us question some of our most fundamental beliefs about science.
It's like we took a peek into the heart of superconductivity and found a whole universe of possibilities, a place where energy might work in ways we can't even imagine. This paper, by making us really think about our assumptions, has opened up this incredible new path to explore, a quest to understand these mysteries of the universe.
And that's what makes science so amazing. The more we learn, the more we realize we don't know, and it makes us want to explore more. Ask those what-if questions that might lead to the next big scientific breakthrough.
So to everyone listening, we'll leave you with this. As you're going about your day, remember that the world is full of mysteries, full of things that challenge what we think we know. Be open to the impossible. Who knows? You might just stumble onto the next big scientific discovery. Thanks for joining us on this deep dive.